All right, so today we're covering 8.3 and 8.4, and this is the last lecture before your exam. Today we're going to talk about springs in equilibrium. So far we've talked about torque in equilibrium, and so I've got the question for you: what happens when you pull a spring? Well, the answer is you stretch out the spring, you increase its length, but the spring also pulls back on you with a force that is equal and opposite to the force with which you pull. Okay. We call this the force of a spring, or the restoring force. So if I compress a spring, it's going to push back and try to go to equilibrium. And if I pull a spring away from its equilibrium point, like the picture shown here, then that spring is going to pull back on me with an equal restoring force to the force that I use. When we're talking about the force of this spring, we can talk about it in terms of a couple of things, right? And so I know just from life experience that if I pull a spring just a little bit, well, it only pulls back a little bit. But if I pull a spring really far, then it pulls back really far as well. And so the farther that I get a spring from its equilibrium point, from its happy spring state, the greater the force that spring is going to exert on me. And so we talk about this as a delta x. Delta x is the distance from its equilibrium length, its happy spring length. And so if I pull a spring 3 centimeters to the left, then in this formula I would call that 0.3 meters, and it's a negative because I'm moving to the left, right? We remember that from the first few chapters of this book. This K here, though, is an interesting thing that you haven't seen before. This K is a variable that represents a spring constant, and the spring constant is unique to each spring. It's the amount of springiness, or you could maybe think of it as like stiffness of a spring. And so a spring with a K constant of 1 has a lot more give to it than a spring with a K constant or a spring constant of 3. The spring with a spring constant of 3 is going to be a lot harder to stretch or compress than the spring with a spring constant of 1. In a given problem, we will either tell you the force and the distance, and you have to find the spring constant, or the spring constant will be given to you along with one of these other values to calculate it out. In science, we use springs for a lot of things. Particularly, we use them for scales. Today in class, I'm going to show the students a spring scale. And when you get back on Wednesday, I can actually bring that out again and show you. But basically, a spring scale, oftentimes we use these to weigh hanging objects or like fish in harbors. And so you put your object on the end of this hook, and it stretches down this spring, and it'll give you a reading on the scale of, oh, whatever this is 50 kilograms or 50 newtons or 50 pounds. And then these scales can measure a lot of different things, so always look for a unit. This particular picture doesn't have one. A bathroom scale also uses spring and spring constant and Hooke's law to tell you how much you weigh, right? And again, this is how much you weigh. It's not telling you your mass exactly, it's telling you your weight on Earth, because springs measure force. And so when you stand on your bathroom scale, you push this lever down, and it's connected to a spring that it pulls down as well, and then this, how much it pulls down, kind of rotates this wheel and tells you how much you weigh on Earth. If you were to take a bathroom scale to like Mars or Jupiter or wherever, it's not going to tell you your mass. It's going to tell you your weight, right? What you feel like. And so if you take a spring scale to Jupiter, then it's going to tell you that you weigh lots and lots of kilograms, when that is in fact not the case. That's where we come into the problem of this misnomer between weight and mass. But on Earth, all of this works just fine. All right. The interesting thing about springs is that we do use them, right, in scales, but they're also a really good model for the atomic level of materials. And so springs and squishy and bouncy things, right, we know they exert a restoring force, like a trampoline or a rubber band. But what about rigid materials in our lives, like the chair that you're sitting in, or the desk in front of you, or a steel cable? Those things aren't so springy, but they do support other things. And so when I exert a force on a rigid object, which means a non-flexible, non-bendy object, on the atomic level, we can think of those chemical bonds as little tiny springs, right? And the force that those exert is equal to this thing called Young's modulus. This is a constant, and it's specific to the type of material that you're using. Any good climber knows that some ropes are better than others, and steel cables are better than any rope around. And so the Young's modulus depends on the kind of material that you're using, as well as the area and the length of that material. And so if I have a, let's say I have two ropes, and one is a much larger diameter, a much larger area, which one's gonna exert a greater restoring force? Well, the one with a larger area, according to this formula. If I talk about the length of these two ropes, and one is short and one is long, well, the longer the rope, the smaller the force that is a restoring force on that rope. And then we talk about the change in length. So after this force is applied, be it your weight or something hanging, that material will stretch a little bit, a lot like a spring. But we already know just from life experience that these are going to be much smaller values than the values that we see with the spring. These rigid materials don't stretch a whole lot before they break. So I want you to take a second and take a look at the Young's modulus on page 242 for rigid materials, and then 245 has two tables for biological materials. Things like bone, which is a really important tensile strength problem, or spider silk, which we all know is really, really strong from Spider-Man, for instance. And so I want you to use this formula. The F equals the Young's modulus for that formula times the cross-sectional area divided by the length and multiply by the length of that thing changes to find the restoring force. Now, it's also good to know that if the force I'm putting on this exceeds the restoring force of that material, well, then that material is going to break. I've exceeded its limit. Right? And so using these few tables, I want you to estimate how many elephants could one of the challenge course cables hold. And I will tell you that the challenge course cables are made out of steel. They're steel cables. And so we'll look on page 242, and I see that steel has a Young's modulus of 20 times 10 to the 10th, and the unit on those Young's modulus is newtons per meter squared, right? How much force can that thing hold per square meter? And so let's make some estimates. I know that the Y for the steel equals that 20 times 10 newtons per meter squared. So I've got the Young's modulus. Good. Now I need the area and the length. And so let's say that each one of those cables has a diameter of 1.5 inches. We can call that, let's go ahead and talk about centimeters. Sorry about that. Let's say that each one of those cables has a radius of 1.5 centimeters. All right, and we'll guesstimate a length on those cables as well, and we'll say that each one of those cables has a length of, I don't know, 10 meters maybe? Does that sound about right? Sure, we'll go with 10 meters. right? And so how many elephants could that cable support? When I talk about something breaking, I'm going to need another important piece of information on page 243, and that is the tensile strength, right? And so this is the very maximum that that a material can hold. And the tensile strength, and I'm just going to call this T for steel, is 1,000 times 10 to the 6. So 1,000 times 10 to the 6th, and again that's in newtons per meter squared. Woo! I know from reading that the tensile strength of something is equal to the force over the area of that material, and so I can find the force that material would support, and so I kind of just plug in values here. I'm going to solve for F, so F is going to equal the tensile strength times the cross-sectional area, and so I'm going to have 1,000 times 10 to the 6 times, and then pi r squared is the formula for area, and I'm going to do pi times 0.015 squared, that's the radius, right, in meters. And then when I get that, once I calculate that value, I will find the maximum force that cable can hold. And I find that value to be 225 with 3 zeros, right? And so I'm looking at 225,000 newtons of force. But that's not what I asked. I asked how many elephants could this thing hold. And so the weight of one elephant is 5,000 times 9.8, which is 4,900, 4,900 newtons. And so to figure out how many elephants this cable can hold, I will take its very maximum amount of force and divide by 49,000. So I'll take 225,000 divided by 49,000, and I find that I could hold about 4.5 elephants. And so we'll just say that this thing could hold 4 elephants with a radius of 1.5 centimeters. So steel cables are pretty tough. And so I've got one last problem for you, and you'll do it much the same way. How many elephants could Spider-Man, dangling from a bridge with a cord of the same length, hold? And so imagine that, okay, now I've got spider silk that is just as big around as that previous problem. And so how many elephants could that hold? And you'll use the tensile strength of spider silk on page 245, which again is 1,000 times 10 to the 6th. You can go ahead and pause it here to work out that problem, and after you're done, this is your homework for the day. Get ready for an open book test on Wednesday for chapters 6, 7, and 8.